I guess. So I will present now the ion trap part of our collaboration and talk about a topic we have already heard about today from actually Andreas in some respect, but I think there are a few differences. So I'm going to talk about how one can envision to use such a quantum simulation device, and in this context it will be a trapped ion device to actually study some aspects of energy transfer in, for instance, molecules such as light harvesting complexes. I want to stress really this word aspects really. We are by no means claiming that we want to study the full molecule, but it's interesting to get behind the physics and actually understand how these things work, and actually from these things works, and actually from a physics point of view, I think this is the more interesting question. So, okay, so I will skip briefly through the motivation. Andreas has really done a great job explaining the physics a little bit, what, how, or not maybe how, but why it's interesting actually to study the energy transfer dynamics in light harvesting complexes. There are also questions like, how is this energy transfer, why is it directed? And Andreas also mentioned briefly that our smell may actually rely on a similar mechanism, where if a donor and an acceptor side, which are detuned with respect to each other, so energy cannot flow from one side to the other without an environment. And the idea is if now a molecule with just the right properties comes along, it can actually mediate such a transfer. And actually it turns out that it depends on whether, for instance, this atom here is deuterium or hydrogen, and we can actually, our smell supposedly can distinguish those two molecules. So how do we want to go about this? We want to basically mimic this kind of physics in an ion trap quantum simulator, where we have, for instance, an initial site corresponding to the donor site and a final site, a target site, with a different energy. And if you want to connect to theorists, it's actually helpful to speak Hamiltonian. So I wrote down here the corresponding Hamiltonian. You have some coupling between the two sites, mediated by some sigma minus, sigma plus interaction with a tunneling matrix element J, and then some detuning between the two sites. So the idea now is to make the system increasingly more complex to get behind the physics, what is happening at these things. So the first thing, if you have just this side, these two sides, you see that energy cannot transfer from one side to the other, so you need something else. And this something else can be, for instance, the environment here represented by a harmonic oscillator with a specific frequency which is coupled to, for instance, the target site here. And now you can imagine is this energy can transfer to this side over by splitting up, so to speak. Part of the energy goes into the target site, but this difference energy can be made up by the environment, and this is how the environment can actually start to enable energy transfer. And you can actually see, or from this simple intuitive picture, you can see if the structure of the environment is not right, this is not going to work. So you need somehow the quantization, if the environment is quantized as it is here, if the quantization is about right, you expect actually that this energy transfer can take place. So here's what we want to do is take two ions and then use standard methods which we have learned from in order to build a universal quantum computer. A lot of research effort went into actually learning how to implement a coupling between two qubits, or the internal states of the ions. And what we add on is the motional degree of freedom of the ion chain, for instance, this ion moving up and down. So those are the degrees of freedom we want to play with. Here, again, now the full Hamiltonian. You have the harmonic oscillator represented here, or maybe I should discuss it here. So this will represent the environment coupled via this force term to the target site, and then we run essentially a quantum gate like Peter Mounts has described in his presentation about 2 hours ago between those two sites. What we do experimentally, and this is important if you want to scale up to larger systems, is just apply a bunch of laser beams. So here these black laser beams implement this hopping between those two sides. These red laser beams, this pair of red laser beams, implements this coupling between the target side and the vibrational mode, and this single laser beam here can shift the energy. So this allows you to play, adjust the knobs of this Hamiltonian, and if you do it right, you can actually get these situations. So what is plotted here is the transfer from one side to the other side, and you can see if you get the detuning right in this instance, and you plot it as a function of the mode frequency, you can see this peak, and that corresponds to exactly this situation when this energy here was just about right. So the strength is that we actually can control all these parameters of the Hamiltonian within some reason, and then you can look at the physics of this very simple model. So in our case, it's a really simple model. It's just two sides and a harmonic oscillator attached to it. So the first thing I talked already about, that the detuning and the bath frequency need to match the structure of the bath. It turns out that also, and Andreas showed this in his experiments, is that the quantum state of the bath, or the temperature of the environment, matters. So if the temperature is very low, the bosonic enhancement doesn't work very well, and you don't get a lot of energy transfer. But as you increase the temperature, you can see here that the energy transfer efficiency goes up, and there will be a maximum if it gets too hot, and you can actually try to understand this a little bit more if you think more carefully about it. On the right here, I plot a 2D plot where this coupling strength is really varied, and where you can actually see this nicely, that here you have resonance, and then the energy transfer goes up, indicated by the colors, and then it tapers off. In an experiment, in a quantum simulation experiment, you can have also negative frequencies. I'm unsure what that would mean in a real system. And what you can see also here, that's interesting, is a subharmonic, so indicating that actually the physics at play is actually rather complicated. Yeah, so I talked already about that we can control these. Of course, what we want to do is we want to get more realistic. So this is just a toy model where I showed you some preliminary data. A real molecule is much more complex. You have many, many modes, and there's also a frequency distribution, so dephasing happening. The way we can get at this is simply by broadening our laser beams, coupling the modes. So essentially what we would have to do is we would have to stick in an additional laser and just apply frequency noise to this laser. Okay, with this, I want to summarize. We have seen vibration-assisted energy transfer in this system. There's a rich physics to explore. And at the moment, we are working on technological improvements which allow us to make a really predictive simulation, not just observe the phenomenon, but really knowing what exactly we do. And that will also be the basis to scale to more and more ions to, for instance, get at 8 sites or see directional energy transfer. So here you can see the recent progress. We increased the trap frequency and their stability. We improved the laser intensity, noise, cut down a lot on it. And especially, we improved a lot about the motional coherence of these states. And finally, I want to flash up my collaborators, Dylan Gorman, who's the lead graduate student, and also mention our theory collaborators. One happens to be the chair of this session, Brigitta Whaley, and Amouran Sarowa, who actually explained us actually why it's interesting to study vibrational energy transfer. Okay, with this, my part, we're done. Okay.
So you're pointing to some differences between the artificial systems that we might synthesize at that point, at least in the lab, and some real material. So, for example, if one is wanting to emphasize the electronic phase transitions, interactions, transport, magnetism, and so forth, you know, we would study, let's say, models which lack phonons. That's basically what you're saying. The lattices that we're working with are ones there where the lattice is imprinted from without, and by and large, the motion of the itinerant particles, in this case, the atoms, don't influence the phonon background. So if one wanted then to go and study additional properties of materials, so let's say in the absence of phonons, we see whatever it is, and you want to see whether now we've added some, you know, ohmic phonon bath, whatever happens to the conclusion. Okay, so we'd have to now dress up the simulation with some extra feature, some extra hardware, if you will, and understand how to do that. So there are methods to add another sort of bath of things. There's ideas of immersing a gas of, let's say, fermionic objects, which represent electrons, immerse them in a bosonic superfluid, which can convey sound modes, which, you know, and the atoms moving around, basically the bosonic atoms and how they distribute themselves changes the potential in which the fermions move. So that's a little bit like variations in a crystal. There's also suggestions for doing these experiments, and we have some work on this in my own lab, within optical resonators, so that the optical lattice is formed in a way that is dependent on where the atoms are located. And then that actually does allow the crystal to move dynamically in response to the itinerant particles. I think in the ion systems, you know, once Hartmut's work, as you saw, was focusing on adding the motional degree of ions back into the ion trap simulator. So whereas for just the simulation of spin systems and the path toward quantum computation, maybe you want to make use of phonons, but basically adiabatically get rid of them because they just enrich your state space in a way that you don't want. Hartmut has been regarding the degrees of freedom as an extra resource, and in particular, if you think about this, that particular application which you spoke of, you know, there's a new application of ion trap systems, where generally where the phonons represent some well-controlled bath in which a many-body quantum system might evolve. So that opens a certain number problem space for you to examine.